Chapter 3.7 focuses on optimization problems. And so these are a series of story problems where we kind of ask ourselves really important questions. Like if you're a farmer building a fence, how big does it need to be to maximize the area of your fence? Okay, so farmers probably don't think or worry about this. But it is true that there are lots of industries, lots of places in the world where this is super important. So for example, if you are running a factory, you might want to find out how to make your boxes that you put your products in. You might want to find out how to make your boxes contain the most product using the least amount of surface area possible, because then you can use fewer materials and put more stuff inside of it. Or similarly, or similar types of things. So there are lots of optimization problems out there. The ones we will do are kind of grossly simplified because we have to be able to finish them in 5 to 10 minutes. Whereas in real life, these can get really complex and have a lot of things going on. But okay, I've read through the problems. 2 of the problems I decided I didn't like, number 5 and number 9. So you can skip those when you do your homework. The rest of them, I think, are all the types of things that we'll do and that you can expect as we go through the course of this semester. So do the rest of those problems and we'll work on it. So what am I going to do? Well, I'm going to start off by just solving a problem. So let's start with exercise 3.25. And in this one, we have a farmer wants to fence in a rectangular space next to his barn. So here's my farmer's barn, and the farmer wants to fence in a rectangular space. That means he's going to take a space here and fence it, but then 1/2 of the fence will be the barn. Ideally, I would make this kind of 3-dimensional, but I'm not very good at drawing, so let's just leave this here. Okay, there you go. There's my 3-dimensional shape. Okay, so but the farmer has a fence here, and the barn is one side of the fence. So he has 100 feet of fence. So what's the largest area we can enclose? So the first thing we're going to do, just like when we did the story problems earlier, is we're going to take this picture and we're going to try to label it as what I call a moving picture. So I'm not thinking of this as a single rectangular fence. I'm thinking of it as all of the possible rectangular fences. So for example, he could have made his fence skinny and wide, or he could have made his fence narrow and long. So these are both options for his fence. And so this isn't meant to represent any individual fence, it's meant to represent all of them. And so every fence would have this basic shape. And then I'm going to label the things that are changing. And what you'll find is that this side here is changing and this side here is changing. So as we make all of our different fences, we have different numbers here and different numbers here for X and for Y. Okay, so I've got X and Y. So that's my first step, is to draw my picture and label it. Once I have a picture and I label it, I become interested in the question that is, what is the largest fence that he can find? And so the largest fence they can find is the area. And we know that in this problem, the area is pretty simple. The area is simply X times Y. Well, what I would like to do is do a little bit of calculus and take the, and find out where this has a maximum. But what you'll see is that that I can't do that because this has 2 variables. It has both an X variable and a Y variable. So this has 2 variables. So I need just one. So I need just one variable. So what I need to do is somehow substitute or make a replacement to change out one of those 2 variables. And that's fine because I have a very natural replacement. My natural replacement is in that second sentence where he says he has 100 feet of fence available. So I know that 100 is equal to the total amount of fence. And how much fence does he use? Well, he uses Y plus X plus Y. So X plus 2Y is the total amount of fence he has. So here's our fence, and this is our fence in X and Y. So now what I can do is I can substitute. So what I'm going to do is I'm going to solve for one of these 2 variables. Let's solve for, how about solve for X? That sounds good. And so what I get is that 100 minus 2Y equals X. And so I can now take this and substitute it right here and now have an equation that I can do a little bit of math with. So I'm ready to write the area is equal to, now instead of X times Y, it is 100 minus 2Y times Y. And my problem now becomes my area is 100y minus 2y squared. And I'm ready to start going about solving this problem. So now that I'm here, how do I find the maximum area? The way I find the maximum area is by taking the derivative and setting it equal to 0. So now I use calculus. And what does it mean to use calculus? Well, we know that this function, whatever it is, will go up and go back down and have a maximum, and that maximum will occur when the derivative is 0. Well, it'll occur at one of those critical points, which could be where the derivative is 0 or where the derivative doesn't exist. In this problem, we're not going to have any fears of the derivative not existing because you see it's just a nice quadratic. It's a nice parabola. In fact, you could do this as an algebra problem. So I could give this to an algebra student, and they could skip the using calculus, and instead they could find that vertex, and the vertex would be where it would be. But let's use calculus. So if I'm going to use calculus, I'm going to take the derivative, and the derivative is 100 minus 4y. I'm going to find out where that equals 0, and that's going to give me negative 4y equals negative 100. And so y is equal to 25. And if y is 25, I can figure out what x is, because I know that x is 100 minus 2 25s, and so that means x is 50. And so I now know the size that my barn needs to be. I need to go 25 in this direction and 50 in that direction, and that maximizes my area for my fence. So the farmer's happy now. He's the largest fenced area possible, and his animals are happy because they have the most space to roam next to his barn. Okay, so this is a general picture. One thing you should probably be aware of is, how do I know that this is the answer just because the derivative is equal to 0? Well, the reason why is, if you look at our picture, we know that if I have this 25 here, you can see that to the left of 25, if I were to put in, say, y prime of some number smaller than 25, so if I were to put in, say, y prime of 0, I would get 100. And so that means my function is increasing to the left of 25. And if I were to put, say, a number bigger than 25, say y prime of 50, that one would be, let's see, so if I put 50 in here, that's 200. That is negative 100. And so that means I'm decreasing here. So my function is increasing on one side and decreasing on another side. This one, so we can see that that point, that 25 here, is necessarily a maximum value. So that tells us that we found the largest height and not just some random height. Now, it turns out that this wasn't really too big of a concern for our problem, because we know right at the very beginning that this graph, we know just by looking at A, that A should be a parabola, and it should be an upside down parabola. So we know that whatever point we found is going to be the top of that parabola and is going to be the maximum. But if you're dealing with an equation that you're not sure about, one that's a little wavier, or you're not sure what the shape looks like, it's always good to do your analysis and make sure that the point you're finding is actually a maximum and you didn't accidentally find a minimum instead. Okay, so we have a strategy for solving these problems. The strategy using for these problems has 5 steps to it. The first step is draw a moving picture, and so here is step 1 right here. So the first step, we draw a moving picture, and then step 2 is where we label the picture. So just like last time, I'm going to call this a moving picture, because this isn't meant to be one fence. It's meant to be all the possible fences you could ever draw, and that's why we put variable names, because as we change the fence from one type to another, these two numbers will have to change. So we draw a picture and label it, and then once we draw and label it, we create an equation. And now what's important is this equation is an equation for whatever it is we're trying to find the maximum of in our problem. So if we're trying to find the maximum area, we want to find an equation for that area. If we're trying to find the maximum perimeter or minimum perimeter, then you find an equation for that perimeter. So it depends upon the problem. But you find your equation for whatever it is you're looking for. And then we substitute. So this is where I substituted. And when I substituted, I used another fact from my problem. So usually there's going to be something else in your problem telling you how to substitute and how to create this equation. And this fact case, we had the fact that there was 100 feet of fence. So we could use that fact to solve for x and then to plug in. And once we substitute, we have only one variable, and now we're ready for the last step, which is using calculus. And so here's our calculus step. The calculus step is almost always the same. We take the derivative and we set it equal to 0, or look for where it does not exist. So we're basically looking for those critical points. I think that for our problems, we will almost always have equal to 0. I don't know if we'll ever have does not exist, but it's possible. It's possible to have problems where the derivative doesn't exist. I think the only time we're going to get things where the derivative doesn't exist is when we're in situations that would kind of have no real physical meaning anyway, right? It might be a case where you draw your fence and one side of your fence is 0, and you go, well, that doesn't matter anyway, because that's not something you can physically make. But okay, we'll find the derivative and set it equal to 0, and then sometimes we'll verify this is a max or a min. So that's what I was trying to do right here. Verify that the answer we're looking for is in fact a maximum or a minimum. Make sure that it's the type of point that we're looking for. I don't want you to get really obsessed with this verifying part, but at the same time, especially if you have more than one critical point, or in your situation where it's unclear if your critical point is a maximum or a minimum value, then you should take a little bit of time to analyze, just like we did in section 3, which one is it? Is it a maximum? Is it a minimum? Okay, so just like in previous problems, what we're going to do is I'm going to stop the video and let you try the rest of the exercises. We have 4 exercises to try, and then I'm going to post solutions to each of those. So try each one and then watch the solution in turn. And if by the end you're getting them right, then that means you're doing really well. The last couple are challenging, so don't get too discouraged if you find them hard. They are challenging problems. But I believe in you, and I think you can do it.